so that takes a few instructions. When you load or you store in the field, that's a set of 4 or 5 instructions. And the last translation is translate to runtime call. So bytecodes which do exceptions, inheritance, and synchronizations are translated to runtime calls. Finally, in the .NET virtual machine, it's using the late resolution of types facility of LLVM, so you could do resolution of recursive types. Here's a set of useful LLVM optimizations that really help producing optimized code. Mem2reg, this will move local variables to registers. So in Java, it's a stack. So in Java and .NET, it's stack-based virtual machine. So you get all these flows and stores. VMKit is a dummy translator between the bytecode to LLVM IR. So it will transcribe this to allocast and then loads and stores. The Mem2reg pass will move this allocast to registers. So that's. I think I need to thank Chris if it's here. It's not here. Okay. So thank you, Chris. Global value numbering really helps also because it will load constant values only once. For example, in Java, the length of an array is constant. So each time you access a field in an array, Java inserts runtime checks if the access is not out of bounds. So you access the length of the array. So this global value numbering pass will make sure that all the length is only loaded once. And I have to thank Owen for that. The predicate simplifier pass will remove some array bounds checks. So is Nick here? Nick? He's not here. Okay. So thank you, Nick, for that, because it removes a lot of array bounds checks. When I talked to Nick about this pass, he told me, well, this pass. So no one's working on this pass right now, and he told me this pass actually is not really useful because coders don't do if 1 is less than n, then if 0 is less than n, etc. Coders don't do that. And actually in Java, there's this implicit runtime checks on array bounds that insert this kind of instructions. So predicate simplifier really helps a lot of removing these array bounds checks. And finally, just to thank Chris another time, loop invariant code motion pass will remove constant values out of a loop, and for Java code, that's great. Okay. So what you all want to hear, performance of VMKit. So we did a set of benchmarks for the JVM on this machine. We compared to 4 other JVMs, OpenJDK, which is Sans implementation, IBM J9, which is one of the best JVMs in the industry, performance talking. The JAX-R VM virtual machine, which is led by IBM, which is written in Java, and the Kakao virtual machine, which is has the same amount of developers than VMKit. We used 2 benchmarks: the Java Grande Forum benchmark, which benchmarks low-level operations and scientific applications. The Spec JVM 98 benchmark will benchmark real-world applications. So for low-level operations, so on all graphs, it's relative performance to VMKit, and so higher is better. For example, if you get a score of 2, you're 2 times better than VMKit. So here we're doing great. Arithmetic operations, LLVM is really generating optimized code. So that's great. For local variable assignment or field assignment, we're doing good too. The IBM J9 is like the most efficient JVM, so and they spend a lot of time in optimizing it and knowing that VMKit is really only developed by me, so that's good. That's really good. Now, what's bad? Not bad, but okay. Low-level operations where we have bad performance. Exceptions are not, exceptions compared to other VMs. It's like OpenJDK is 24 better. Allocating memory, other virtual machines do really better than VMKit. So the reason for this is that LLVM doesn't do any optimization on exceptions, and we're actually using GCC's unwinding code. So, well, since LLVM is a friendly community, I won't say that GCC's unwinding code is crappy, but well. For memory allocation, we're using the BOEM GC allocator, which is a conservative allocator. It's the same. Kakao is also using the BOEM GC, so that's why we have comparable performance. In the case of GC in virtual machine, conservative, it's bad. You should use generational garbage collector. So that's why we don't perform well here. Okay, so for scientific applications, we're good. Series benchmark, we're better than the other ones. For the other benchmarks, heap sort crypt, FFT, and sparse matmult, 1.5. The industrial JVMs like OpenJDK and IBM J9 are 1.5 better. So that's really good for us. For the LUFACT and SOAR benchmark, so LUFACT, we're having worse performance because in LLVM there's no escape analysis. So in escape analysis, instead of allocating your objects on a heap, you allocate them on stack. So you don't need to have this. You don't need to lock your memory allocator and allocate the object. So you allocate on stack, and you get better performance. For the SOAR benchmark, that's because of well, Nick's not there, so that's because of the array bounds checks, the predicate simplifier pass, which is not really optimized, optimized fashion right now. So it's missing some array bounds checks it could remove. So that's why we have low performance than the other JVMs. For real-world applications, for the spec JVM 98.